Good evening and welcome to GER Hub. In this class, I shall be discussing binomial expansion. Okay, as a topic in mathematics, I shall be discussing binomial expansion. Please subscribe to my channel if you haven't subscribed by clicking the subscription button and endeavor to turn on your notification bell. Okay, and please also do well to join the community on YouTube, my community on YouTube, by clicking the join button to join the community on any level of your choice. Please do that for the channel and drop a like on this video. Thank you very much. Let's begin. So let's start this video with one problem students usually face. So I'm going to start this video with number one, a problem that students usually face in expansion. So let's take a problem like this. Let's assume that you were given 2x plus 1 all squared to expand. Now, one thing students would usually do, students especially who are not aware of a technique called binomial expansion, what students in that category would usually do will be to use their common knowledge of indices to say 2x plus 1 in one bracket multiplied by 2x plus 1 in another bracket. Now, the question is, are such students wrong? The answer is a big no. They are not wrong. Now, why they are not wrong is simply because 2x plus 1 all squared, according to indices, tells you that you have to multiply whatsoever is squared twice. So if 2x plus 1 is carrying the power 2, it means that you should multiply 2x plus 1 by its own self 2 times, and that would give you this times this. So those students are not wrong. Now, in doing that, using the simple basic routine from indices or expansions in algebra, we are told that the first value would have to multiply the second value. The first value in the first bracket will multiply the first value in the second bracket. Okay, so 2x would multiply 2x. And thereafter, you would use the same 2x to multiply the second value 1 in the second bracket. And that would mean plus 2x times 1, then plus again. We were told that once you are done using the first number or element in the first bracket to multiply the first and second respectively in the second bracket, you will now start using the first or the second element in the first bracket to do the same routine. That is using 1 to multiply 2x and then using the same 1 to multiply 1. And you can now summarize your result as 2x times 2x gives you 4x squared plus 2x times 1 is 2x, 1 times 2x is 2x plus 1 times 1 will give you 1, and this will summarize to 4x squared. 2x plus 2x can add to each other, so this will give you 4x plus 1. This will be the result you would get if you were to carry out that expansion normally. Now, question number 1 is this. In such a problem, if you were to be given 2x plus 1 all raised to power 7, it was easier to solve this problem because the power was 2. What about a case where the power is as large as 7? What would the answer be to that expansion? That is the first question. The second question is, what if in that expansion or in this problem, the interest is not in getting the expansion, but in determining one term in the expansion or the coefficient of one term in the expansion? Would you go on using such a process? Because if you are to use this knowledge of 2x plus 1 squared in solving a problem like this, then funny enough, students may end up doing something like this. That is multiplying 2x plus 1 by itself 7 times according to indices. And that is where the idea of binomial expansion comes in. Now, what would we be doing in this particular video? For you to study binomial expansion, there are certain things that need to come first, implying that the first thing we shall be discussing, although under this topic binomial expansion, is what is the relevance of binomial expansion or expansion techniques. So the first question we shall be answering, now that we know that this particular technique is not sustainable, the first question we shall be answering is why or what can techniques of expansions do for us. So the first thing you need to know is that techniques of expansion would help you, number one, save time. Okay? So rather than doing this, expanding in this manner, if you use a certain technique for expansion, you would save time. 2, it would eliminate complexities. So complexities in expansion will be eliminated. To eliminate complexities in expansion. So rather than do all this in working through complex methods of expanding repeatedly, the 2x plus 1 times 2x plus 1 times 2x plus 1 times 2x plus 1 until you get to 2x plus 1 the 7th time, it will help you using an accurate or a more efficient expansion technique would help you eliminate complexities. 3, using an expansion technique, as you would see in this video, will help you also to predict terms or coefficients of terms. In an expansion. Okay, so not all the time in a particular question on expansion do we require you to tell us the expansion for a particular binomial expression. No, sometimes we just need you to predict a particular component of that expansion or the coefficient of that term in that expansion. Number 4, an expansion technique would help you do the basic thing, which is to expand. Okay, now please take note. Why is it called? There are 2 techniques. Let's start with techniques of expansion. Now, under this topic called binomial expansion, we shall be looking at 2 basic techniques. The number one technique we shall be looking at is the technique called Pascal's triangle. Pascal's triangle. The second technique is the binomial expansion technique. Okay? So the Pascal's triangle technique and the binomial expansion techniques are 2 techniques we shall be discussing in this video. Now, that being said, let us start with the first technique, being Pascal's triangle. Pascal's triangle. Okay? Now, before we begin with Pascal's triangle, guys, the first thing I want you to take note of is that these 2 techniques have something in common. Both of them do not necessarily help you expand directly. They only help you in determining the coefficients. They help in determining the coefficients of terms in an expansion. So if you are using Pascal's triangle technique or you are using binomial expansion technique, basically these 2 techniques will help you determine the coefficients of terms in the expansion. Okay, so that's what basically both of them will do for you. The rest will require your input. So Pascal's triangle, binomial expansion technique would help you determine the coefficient of terms in an expansion. Now, you've heard me say binomial, binomial, binomial. So a binomial can be looked at. Let's start with that. A binomial in this case is a two-termed expression. Is a two-termed expression, implying that an expression such as x plus y constitutes a binomial. Okay? So, any expression that contains two terms, such as 2x plus 3, such as 4x minus 5, such as 2x squared plus 6, any expansion like this, any expression rather like this, having term 1, term 2, term 1, term 2, term 1, term 2, term 1, term 2 can be treated as a binomial. So we would look at a binomial as being a two-termed expression. Now, when does expansion come into play? So if a binomial is a two-termed expression in this particular topic or in this particular sense, putting a power to this two-termed expression, such as all in brackets x plus y raised to power 4, or putting a power such as 2 to this, putting a power such as 5 to this, putting a power such as 6 to this, now makes room for what is called an expansion of this binomial. So it is the expansion of a binomial expression carrying different powers that we are interested in this discussion on binomial expansion. Now, for you to understand or appreciate binomial expansion, it is best we start with going through Pascal's triangle as a technique of expansion, which will ultimately lead us to the binomial expansion technique. So let us go to Pascal's triangle. Let's go quickly to Pascal's triangle. So now let's go back to a basic thing. Let's assume we have x plus y all raised to the power of 0. If you were given x plus y all raised to the power of 0 in indices, we were told that anything raised to the power 0 in indices gives 1. Okay? Now, if you move ahead from x plus y raised to the power 0, such that this binomial x plus y carries a power 0, giving you 1 by indices, we were also told from indices that anything raised to the power of 1, so if this binomial carries 1 as its power, the expansion will give x and y, carrying coefficients 1 and 1 in addition. That is what you would get, because x plus y raised to the power 1 returns x plus y according to indices, and the coefficient of x and y in that expansion will be respectively 1 and 1. If you proceed again to x plus y raised to the power 2, you would end up having this expansion 2x x squared plus 2x plus y squared. And how would you obtain this? It will be from x plus y multiplying x plus y like we did earlier on. X multiplying x to give you x squared, x multiplying y to give you 2, this should be 2xy, sorry. So x multiplying y to give you xy, and the y multiplying x to give you xy again, added together giving you 2xy, and y multiplying itself to give you y squared. Now, what am I trying to say? In the end, you would discover a pattern for the coefficients of this expansion. If you proceed further to x plus y raised to the power of 3 in this particular order, you end up having the coefficients of that expansion to carry 1, 3, 3, and 1. Notice one thing. In the expansion of x plus y raised to the power of 0, you had just one term as the result. In the expansion of x plus y raised to the power of 1, you had two terms, meaning that the number of terms that emerges from the expansion is 1 plus the power. So if the power is 1, you have two terms in that expansion. If the power is 2, you have three terms in that expansion. 1, 2, 3. So if the power is now 3, you would have 3 plus 1 terms in that expansion. 1, 3, 3, and 1. So let's look at it again. So according to Pascal's triangle, what is called what the coefficients of an expansion will be. For an expansion that carries the power 0, the coefficient will be 1. For an expansion that carries a power 2 or a power 1, the coefficients will be 1 and 1. For an expansion that carries the power 2, the coefficients will be 1, 2, and 1. For an expansion that carries the power 3, the coefficient will be 1, 3, 3, and 1. Now, from these we have done, you will notice this pattern emerging. Now, notice one thing. I could add, let me use a black pen here. I could put a plus on each side. 1 plus 0, an imaginary 0. 1 plus 0 to the left gives me 1. So 1 plus 0 to the right gives me 1. If I add an imaginary 0 here again, and add another imaginary 0 here, you will notice that 1 plus 0 gives this 1. And if I put a plus here, 1 plus 1 gives this 2. Okay? So, you could start seeing a pattern. For me to get 3, 1 plus 2 gives 3, 2 plus 1 gives 3. And if you put an imaginary 0 here, of course, this gives 1. And if you do that here, of course, this gives 1. Now, what it means is that, to start with, Pascal's triangle shows you that the coefficient of successive expansions is in a triangular form with 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And if you are to go on, you would end up having 1, 4, 3 plus 3, 6, 3 plus 1, 4, and 1 plus 0, 1. If you proceed again, you would end up having 1, 1 plus 4, 5, 4 plus 6, 10, 6 plus 4, 10, and 4 plus 1, 5, and then 1. So, why is this necessary? Pascal's triangle tells you that if you have an expansion such as x plus y raised to the power of 4, it means that in that expansion you should be expecting how many terms? 5 terms. 1, 2, 3, 4, and 5. Now, it is telling you that if you are expecting 5 terms from an expansion such as x plus y raised to the power of 4, take note, you don't need to stress yourself about what the coefficients will be. For an expansion that has a power 4, the coefficients will be 1, 4, 6, 4, and 1. So, whatsoever the result that emerges from this will be, all I know is that the coefficients are already determined by the Pascal's triangle. So I'm going to put 1 here, I'm going to put 4 here, I'm going to put 6 here, I'm going to put 4 here, and I'm going to put 1 here. Okay? Now, I told you earlier on that Pascal's triangle would not help you completely expand. It would only tell you what the coefficients in an expansion should be. Now, that is exactly what it has done for us in this expansion. The next thing I would want to tell you that makes the Pascal's triangle common to the binomial expansion technique is the fact that in trying to now determine what the actual expansion will be, now that Pascal's triangle has given you the coefficient 1, 4, 6, 4, 1, for an expansion that carries the power 4, what you would do is to now take note of certain rules. In an expansion, please take note, in a binomial expansion, there are two variables, the first variable and the second variable. Now, in expanding, you start with the first variable. So I'm going to put the first variable here, x. In this instance, when the expansion starts, it starts from left to right. So you move from the left hand side in an expansion to the right hand side for the two variables. Now, when the expansion starts, the first variable carries the highest power of the expansion, which is 4. So you put x raised to power 4 here. In that case, if x, the first variable, carries the highest power 4, the second variable y will carry the the lowest power, which is 0. At all points in the expansion, the total power here must be equal to the total power here. So 4 plus 0 will give you 4. Now, that is the first stage or the first step for the first term in the expansion. If you move from left to right in that expansion, the first variable again will come in here, and its power, whereas it was previously 4 for the first term, will drop by 1 to 3. So it will drop from 4 by 1 to 3, and because it has dropped to 3, the power of the second variable will increase from 0 to 1. Okay? Now, if you move a step again into the expansion from left to right, the expansion would have x carrying this time around 2 because it will drop by 1 again, and y will carry the power 2 because it will increase by 1. And if you move a step further again, this will be x raised to the power 1 because it will drop by 1 again from 2 in the expansion from left to right by 1, and y at this point would increase from 2 to 3. Take note, at each point, the total power here amounts to 4. 4 plus 0 is 4. 3 plus 1 is 4. 2 plus 2 is 4. 1 plus 3 is 4. So, you can now guess what x will be at this point in the last term of the expansion. It will be 0 because it will decrease by 1 again. And at this point in time, y would have increased by 1 from 3 to 4. Again, 0 plus 4 will give you 4. So, this requires your knowledge. It requires your adherence to rules. It requires your understanding of the instruction or understanding of the law that as you progress from left to right in an expansion, the power of the first variable, starting with the highest power, keeps decreasing by 1, while the power of the second variable, starting with 0, keeps increasing by 1 to the highest variable. Okay? So, this is Pascal's triangle. Now, I'm going to use Pascal's triangle to solve several problems here before we go into binomial expansion. Okay? So, let's use Pascal's triangle to solve few problems. Now, let's expand this 2x plus 1 raised to the power of 3 using Pascal's triangle. Let's expand 2z squared plus 3z. Let's expand this raised to the power of 4 using Pascal's triangle. Let's do that using Pascal's triangle. Okay? Now, finally, let's also expand a plus 2b raised to the power of 7 using Pascal's triangle. And this last example would show you what the disadvantage of Pascal's triangle is. So for number 1, 2x plus 1 all raised to the power of 3. Now, all I would do here, before you start using all of them for Pascal's triangle, let us develop Pascal's triangle quickly for the problems we shall be solving. So, I'm going to start with 1, 1, 1. 1 again, 1 plus 1, 2, and 1. I'm going to proceed to 1, 3, 3, and 1. Of course, 1 plus 2 is 3, 2 plus 1 is 3, and 1, 1 on the other side. Then I'm going to go again to 1, 4, 6, 4, and 1. I'm going to proceed again to 1, 5, 10, 5, 5, okay, 1, 5, 10, 10, 5, and 1. Okay, now let's expand with this. Starting with the first expansion, 2x plus 1 raised to the power 3. It carries the power 3, so it means the one we shall be using will be this one that contains 4 terms. So I'm going to write here 1, 3, 3, and 1. So what Pascal's triangle has just done for me is to determine the coefficient. So I'm going to put the coefficient here. Then I'm going to move over and bring the first term. The first term in this expansion is 2x, so I'm going to put 2x here raised to the total power, which is 3. I'm going to take the second term, 1, put it here raised to power 0, plus. I'll come to the next. The coefficient has already been determined to be 3. I'll put here 2x, the first term, raised to the power of 2 because it will drop by 1. And I will put here 1 raised to the power of 1 because this will increase by 1 from 0. Plus, I'm going to put here 2x raised to the power of 3 or the power of 1 because the first term will drop its power by 1 again from 2 to 1, and this will be from 1 to what? To 2. So at all points, the total power is 3. Then the last will be plus 1. Let's put here 2x raised to power 0 because it will diminish by 1 again, and then this will be 1 raised to the power of 3. So, what have we just done? We have just obeyed the rules that as you move from left to right in the expansion, the power of the first variable takes the highest power and keeps decreasing by 1 through each term, while the second variable takes starts with 0 and keeps increasing by 1 to the highest power. So, once you do this, you can now simplify. So, anything raised to power 0 is 1. So 1 raised to power 0 is 1. 1 times this 1 will give you 1. And you would have 1 times 2x raised to power 3 by indices will be 2 raised to power 3, which is 8. X raised to power 3. So that will be the first term. Now coming over here, 1 raised to power 1 by indices is 1. 1 times 3 is 3. Hold on to that. Then 2x raised to power 2 means 2 raised to power 2, which is 4. And x squared. So that will be 4x squared times 3, giving you 12x squared. Plus, coming over here, 1 raised to power 2 is 1. 1 times 3 is 3. Now, 2x raised to power 1 is 2x. So, 3 times 2x will give you 6x. Then you come over to the last. 2x raised to power 0. Anything raised to power 0 is 1. So, 1 times this 1 is 1. And 1 raised to power 3 is 1. So, you end up having 1. And that expands this particular problem using Pascal's triangle. Now, let's come over to the second problem using Pascal's triangle. 2z squared plus 3z all raised to the power of 4. Now, if you go back to Pascal's triangle, raised to the power of 4 means that it will have 5 terms. 1, 4, 6, 4, 1. Okay? So I'm going to take the 5 terms here, the coefficients 1, 4, 6, 4, and 1. Now, once I do that, once I've determined the coefficient, why is it 1, 4, 6, 4, 1? It is because in Pascal's triangle, a power of 4 would have 5 terms. Okay? And by Pascal's triangle, the 5 terms will have coefficients 1, 4, 6, 4, 1. So I've written out my coefficients. I will now come over with the first term. The first term in my expansion is 2z squared. So it will be 2z squared raised to the total power, which is 4. And 3z carrying 0. Plus, let me shift this a little bit. So plus 4 is the second coefficient. This will be 4 times 2z squared all raised to the power of 3 because it will decrease by 1 again. Let's bring this down here for more space. So let's start all over again. So I'm going to write here 1, 4, 6, 4, and 1. Okay? So I'm bringing 2z squared. 2z squared all raised to the power of 4 and 3z raised to the power of 0. The first term is 2z squared. It comes in here raised to the power of 4 because it starts with the highest power. 3z carries 0. The second term, it starts with the lowest power, 0. Now plus 4 is the second coefficient according to Pascal's triangle, and that 4 would multiply the first term here, 2z squared, carrying one short of this power, which is 3, because as it moves from left to right to be dropping powers, and the second term would increase by 1 in power. So from 0 it will go to 1, plus the next term has a coefficient 6 according to Pascal's triangle, but it will carry 2z squared, the first term here, having the power drop by 1 again to 2 from 3, and the second one will be 3z raised to the power of 2 because it increases by 1 to 2, plus the next term will carry 4 as the coefficient, and this will be 4 2z squared all raised to the power of 1, and you will have 3z raised to the power of 3 because it will increase by 1 the power, plus, let's bring this one down, 1, which was the last coefficient, times 2z squared raised to the power of 0 because it decreases by 1 again, times 3z raised to the power of 4 because the second term increases by 1. Now, once you get this done, all you need to do finally is to simplify. Now, 3z raised to power 0, anything raised to power 0 is 1. So, I'll have 1 multiplying this 1 to give 1. So, let's bring this down here. 2z squared raised to the power of 4 is what will remain here, because this will multiply 1 and it will multiply 1. So, let's come over here. 4 in bracket 2z squared raised to the power of 3 times 3z, because 3z raised to the power 1 is 3z. Then plus, this is 6 times 2z squared raised to the power of 2 times 3z squared. Okay? Plus, you have 4 times 2z squared. 2z squared raised to the power of 1 is 2z squared. So I'm going to bring this down here. I want us to see everything clearly. So, this will be raised to the power of 3 plus, finally, 2z squared raised to the power 0 is 1. 1 times 1 is 1. 1 times 3z raised to the power 4 is 3z raised to the power 4. So it now looks better. Okay? Now at this stage, you can do your final simplification, which will require you to apply the laws of indices. So 2z squared raised to the power 4 will be 2 raised to the power 4, which is 8. 2 raised to the power 4, which is 16, sorry. 16. And z squared raised to the power 4 will be by indices z raised to the power 8. Then plus 4 times 3 is 12. 4 times 3 is 12. Okay, let's start with 2 raised to the power 3. 2 raised to the power 3 will give you 8. 8 times 4 is 32. Or you could go with 2 raised to the power 3 giving you 8. And 8 times 12. You could choose to multiply that way. So 4 times 3 is 12. And 12 times 8 will be 96. So I'm going to put here 96 for the multiplication of all the constants, and this will be z raised to the power 6 by indices times z, giving you z raised to the power 7. So we are done with that. Come over here. 3z squared is 3 raised to the power 2, which is 9, and z squared. So 9 times 6 is 54. Okay? And 54 times 2 will be 108. So you will have 108 here. Oh, we have to multiply by another 2. This should have been 3 times 3 is 9. So 9z squared. Okay? 9 times 6 will give you 54. This is 2 raised to the power 2. I thought it was 2. So that's 2 raised to the power 2. So it will be 54 times 4. And 54 times 4 is, that is 216. Okay? So 4 times 4 is 16. 4 times 5 is 20 plus 121. That should give us 216. So this should have been 216. Okay? So we'll write 216 there. And z squared raised to the power 2 will be z raised to the power 4. And z raised to the power 4 times z squared will give you z raised to the power 6 by indices. So we come over to the next one. Now for the next one, you have 4 times 2, which is 8. 8 times 3 raised to the power 3 is 27. So 8 times 27 is what we are going to have there. And 8 times 27 is 8 times 2 will give us 16 plus 5, that's 216 also. So this would also be 216. And we will bring the z's. So this will be z raised to power 2 times z raised to power 3 will give you z raised to power 5. So finally, you would end up having 3 raised to power 4 should be 81. And you would have z raised to power 4 when you expand this. So this is the expansion you would get using Pascal's triangle. Okay? Now, where is Pascal's triangle deficient? You can see the deficiency of Pascal's triangle in a problem of this nature. A plus 2b raised to power 7. In doing this, it will mean you have to use the triangle to determine the coefficients for 7, which will mean writing out those triangles again and again. That is developing, let's see, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. This is for 0 power, this is for 1, this is for power of 2, this is for power of 3. This is what I was actually doing. So if you are to tackle this problem using Pascal's triangle, you will have to start developing the triangle until you get to the 7th power, which will contain 8 terms. Now, if you do that, this is for a 0 power. This is for a power of 1, having 2 terms. This is for a power of 2, having 3 terms. This is for a power of 3, having 4 terms. This is for a power of 4. This is for a power of 5. This is for a power of 6. You would have to do for a power of 7, in which case you would have 1, you would have 7, you would have 21, you would have 35, you would have 35 again, you would have 21, you would have 7, you would have 1. Now, this method is not efficient for expanding this, and that is where binomial expansion comes into play. So, to tackle a problem like that is best done using binomial expansion. So, let us now put down the rules in binomial expansion. The rules are not too different from what we already have done in Pascal's triangle. The first rule in binomial expansion lets us know that every coefficient in a binomial expansion is combinatorial. I would explain what that means. It's combinatorial in nature. It's combinatorial in nature. That is the major difference between the binomial expansion and Pascal's triangle. Whereas Pascal's triangle would demand that you use triangles of coefficients to expand, binomial expansion tells you that no, don't do it that way. Just take note of the fact that every coefficient in a binomial expansion you would have used Pascal's triangle to obtain can be predicted because they are combinatorial in nature, and I'm going to explain that. Every other thing remains the same, so let's add to this particular set of properties in a binomial expansion that the coefficients or the variables, the first variable in a binomial expansion, starts with the total power. In the expansion, and progressively decreases by 1 in each term from left to right in the expansion. Okay, so as you move in the expansion from left to right, the total power, the first variable will start in the expansion with carrying the total power, and will keep reducing by 1 progressively as we move from left to right through each term. 3. The second variable keeps increasing by 1 in power. Keeps increasing by 1 in power as we move in the expansion. As we move in the expansion from left to right through each term. So it is worth noting that also. Number 4, at each point in time in the expansion, at each point in time in the binomial expansion, the total power of the two variables must add to give the power of the expansion, like I explained earlier, the power of the expansion. Okay, so taking note of that, let's go over it again. Number 1, in a binomial expansion, the first and golden rule says that every coefficient in the binomial expansion is combinatorial in nature. That's number 1. Check. Number 2, the first variable in a binomial expansion starts with the total power, that is the power of the expansion, and progressively decreases by 1 in each term from left to right in the expansion. Check. 3, the second variable of the expansion keeps increasing by 1 in power as we move in the expansion from left to right through each term. We have already used this in Pascal's triangle. Check. At each point in time in the binomial expansion, the total power of the two variables must add to give the power of the expansion. Check. We've already used this previously. So I told you this is the only difference between the Pascal's triangle and the binomial expansion. Now, let us now equip ourselves. I'm going to recall from the topic called combination and permutation. Just in case you've not done this topic, please go through my videos in the channel to check for my videos on permutation and combination, just to equip yourself with knowledge on combination. So, combination is a selection technique. Permutation is an arrangement technique. I will stop at that. But please take note that in combination, we usually would define a combinatorial process by this expression, N combination R. This is read as N combination R. Okay? If you don't want to write this as N combination, if you don't want to write N combination R as this, there is a vector form for writing the same expression. So if you don't see it in this form, expect it to be written in this form. So when you see NR under combination or binomial expansion, it does not mean we are referring to a vector, a column vector, or a column matrix. Please take note, we are referring to N combination R. Now, what does N combination R mean, guys? I told you earlier on that combination in mathematics is a selection technique, while permutation is an arrangement technique. So, N combination R means selecting R objects from N available objects. Okay? Selecting R objects from N available objects, or spaces as the case may be. So, please take note. What is the definition of N combination R? This is just to remind you. N combination R, which is NR, which can be written as this, is defined as N factorial all over N minus R factorial, R factorial. And just in case I may be speaking to someone who has never done factorials, please take note. N factorial is defined as N times 1 less than N times 1 less than N minus 1, which is N minus 2, times 1 less than N minus 2, which is N minus 3, and so on until you get to 1 times 0 factorial. And please take note that 0 factorial is 1. Okay? So, let's now use actual numbers to do what I'm showing you here. Now, just in case you are new to combination and factorials, this will help you because we need it in explaining binomial expansion before rounding up this class. Now, look at it this way. So if I ask you to select 2 objects from 5, it will mean 5 combination 2, which can be written as 5 combination 2. And by the expression above, this will be defined as, remember when it was n combination r, which is nr, we wrote n factorial all over n minus r factorial. So this will mean 5 combination 2 is 5 factorial all over 5 minus 2 factorial 2 factorial. Okay? Now, please take note of something. 5 factorial, according to what I have just told you in the factorial expression, is 5 times 1 short of 5, which is 5 minus 1, times 1 short of 5 minus 1, which is 5 minus 2, times 1 short of 5 minus 2, which is 5 minus 3, times 1 short of 5 minus 3, which is 5 minus 4, times 1 short of 5 minus 4, which is 5 minus 5 factorial. Okay? And this will give you 5. 5 minus 1 is 4. 5 minus 2 is 3. 5 minus 3 is 2. 5 minus 4 is 1. And 5 minus 5 is 0 factorial, which in itself is 1. So if you multiply all these, 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. 120 times 1 is 120. And 120 times 0 factorial, which is 1, is 120. So this is how to use the expansion and the factorial notation. So if I ask you for 2 factorial would amount to 2 times 1 times 0 factorial, which will give you 2 by what we have said. I hope that is clear. Now, let's now come back to the binomial expansion. Please, you can revisit those things I have just said to make it very clear. Now, let's look at the binomial expansion of x plus y raised to power 2. According to the binomial expansion, the coefficients, unlike Pascal's triangle, are combinatorial in nature. So what do you do? According to binomial expansion, the first coefficient will be 2 combination 0. Okay? So 2 combination 0, and you will have x raised to power 2, the highest power, and y raised to power, you have y raised to the power of 0. So I have just determined my coefficient here. The coefficient, remember, are combinatorial in nature. The next coefficient would have 2, the highest power, combining with 1. Okay? And 2 combination 1 is what you have here. This will be x now. The other rules are obeyed. It will drop by 1, and this will become y raised to power 1. Plus, the next one will be 2 combination 2. Notice that I started with 0, increased to 1, and increased to 2 in the last term. And this will be x raised to power 0 when it decreases by 1 again, from 1 to 0, and this will be y raised to power 2. Now, finally, once you do this, you can now simplify. Please take note. I'm going to give you the following rules. Anything combination 0 is 1. Please take note of that. Anything combination itself is also 1. Okay? So, take note again that anything combination 1 short of itself, that is, anything combination 1 short of itself, would also give you that thing. So, n combination n minus 1 should give you n. Now, let's see why that is true before we come back to this problem. Please, it is very important. If you are using binomial expansion, it's very important. So, n combination 0, we said earlier on, is n factorial all over n minus 0 factorial, 0 factorial. And this will give you n factorial all over n minus 0 is n, so that will be n minus 0 factorial is n factorial, and then 0 factorial. Now, 0 factorial is 1, so this will be n factorial times 1, and that will give you n factorial all over n factorial. times 1, which is n factorial, and n factorial cancels this to give you 1. So it means you don't need to stress yourself when doing a binomial expansion in looking for anything combination 0. Stress yourself with other ones, not n combination 0 or anything combination 0. You also should not stress yourself with anything combination 1 short of itself, just like 2 combination 1. 2 combination 1 is 2, because this is 2 combination 1 short of 2, which is 1. So let's see why that is true again. N factorial all over n minus, in bracket n minus 1 factorial, n minus 1 factorial, and then n minus 1 factorial. Now let's simplify. This will give you n minus 1. N minus, if you expand this, minus times n is minus n. Minus times minus 1 is plus 1. Put your factorial, and this is n minus 1 factorial. So this will give you n factorial all over. N minus n is 0, so this will be 0 factorial. And this will be n minus 1 factorial. Now 0 factorial is 1, so that will be n factorial all over 1 times n minus 1 factorial. This will give you n factorial all over n minus 1 factorial. Okay, because n minus 1 factorial times 1 is n minus 1 factorial. Now, n factorial all over, you can expand this just one step further. Remember, in the expansion process of factorials, n factorial would have been n times n minus 1 times n minus 2 and so on. And n minus 1 and so on can be summarized as n minus 1 factorial. So all over n minus 1 factorial. This will cancel, giving you n. Now, this is to show you again that anything combination 1 short of itself is that thing. So don't stress yourself with that in a binomial expansion. Now let's come to the last one, which is n combination n. Anything combination itself gives you 1. And why is that so? N combination n will be n factorial all over n minus n factorial, and this will be n factorial all over n minus n factorial is 0 factorial, and this will be n factorial. This cancels this, giving you 1 over 0 factorial, which is 1 over 1, which is 1. So that is true. Now let's come back to the problem. So let's come back to that problem. So we had said that this is x plus y all squared raised x plus y raised to power 2, and we say this is 2 combination 0 because the coefficients are combinatorial in nature. This is 2, the power here combination 0, it starts from 0, and x carrying the power 2 and y carrying the power 0 in the first instance. As you progress, this 0 increases to 1, and x will drop from 2 to 1, and y would increase from 0 by 1. And this will give you 2 combination 2 where the expansion stops. When this 0 increases to the total power here, it will stop the expansion, and this will be x raised to power 2, x raised to power 0, sorry, because it drops by 1, and this will be y raised to power 2. So this will give you 2 combination 0. You don't need to stress yourself. What is it? It is 1. X squared, y raised to power 0 is 1, plus 2 combination 1, we said it is 2. This is x raised to power 1, which is x, and y raised to power 1, which is y, by indices. 2 combination 2, we have just told ourselves that anything combination itself will give you the 1. So this will be 1. X raised to power 0 by indices is 1, times y raised to power 2 comes here. So your expansion will be 1 times x squared times 1, which is x squared, plus 2xy, plus 1 times 1 times y squared, which is y squared. Okay, so you see how easy it is to expand using binomial expansion. Now let us proceed to more expansions. Now, using the binomial expansion, let us take this problem now. 2x plus 1 that we did earlier on raised to power 3. Let us use the binomial expansion. So the first combinatorial coefficient will be 3 combination 0. So the power 3 combination 0. That will be the first coefficient, not like the Pascal's triangle anymore. Then you will take 2x, the first term, raise it to the power of 3, the total power. Then take 1, the second term, and raise it to the power of 0. This must add to 3, of course. Plus, the next combinatorial coefficient will be 3 combination 1. So 3 combination 1, this increases from 0 to 1. And this will be 2x raised to the power of 2 because it will drop by 1, and this will increase by 1 from 0. The next one will be plus 3 now, combination 2. This will increase from 1 to 2. This will be 2x raised to the power of, it drops by 1 from 2 to 1, and this will increase from 1 to 2. Take note, the total power at each instance gives the total power here, 3 of the expansion. Then the final will be 3 combination 3 and 2x raised to the power of, this time around it drops from 1 to 0, and this will be 1 raised to power 1 raised to the power of 3, the total power. So that is where the expansion stops. How do you know that the expansion stops there? It stops there because the total combinatorial power is now 3, or the total combinatorial value here is 3. Okay? From 0 to 1, from 1 to 2, from 2 to 3. So it stops there. Now, I don't need to bother myself with 3 combination 0 because I know it is 1 by what I have told you. And 2x raised to power 3 is 2 raised to power 3, which is 8, and x raised to power 3 times 1 raised to power 0 is 1. Plus, come over here, 3 combination 1 will give you 3 factorial all over 3 minus 1 factorial, 1 factorial. And we'll put here 2 raised to power 2x squared will be 2 raised to power 2, which is 4, and x squared. Then 1 raised to power 1 plus, we will now come over here to say, for this one, 3 combination 2 will surely give you 3. Okay? And that is because 2 is 1 short of 3 by what we said earlier on. 2x raised to power 1 is 2x. So I'm going to put 2x here. And 1 raised to power 2 is 1. Plus, then coming over here, 3 combination 3 is 1. Because anything combination itself is 1. And this will be 2 raised to power 0 is 1. 1 raised to power 3 is 1. So you can now simplify all together 8x cubed, because 8x cubed times 1 is 8x cubed, plus 3 factorial all over 2 factorial is what you are going to have here, and that will be 3. When you simplify this, 3 factorial is 3 times 2 factorial, and 3 minus 1 factorial is 2 factorial, so that 2 factorial will cancel the 2 factorial. That is, this whole thing here is 3 factorial, 3 times 2 factorial all over 2 factorial, that is 3 minus 1 factorial, which is 2 factorial times 1 factorial. This will cancel this, and 1 factorial is 1. So 3 over 1 is what you have, which is 3. Times 4x squared times 1. So this will give you 3 times 4x squared. And this one will give you 3 times 2, which is 6. So this will be 6x, and this will be 1. So if you simplify further, this will be 8x cubed plus 12x squared plus 6x plus 1. So this is a foundational class on binomial expansion. In my next class on binomial expansion, being the second class and probably my last class on binomial expansion as a topic, I will be showing you 2 things. I will be showing you how to solve more complex problems on binomial expansion, and I will be showing you how to use binomial expansion in approximating values. Thank you very much for watching this 1-hour class with you. It was a nice time. Please subscribe to my channel if you haven't subscribed. Like this video, share this video, and do well to join my community on YouTube by clicking the join button and proceeding on any level you find comfortable for you. Thank you very much, and have a blessed day or a blessed night wherever you're watching from.